Welcome to another edition of Math with Taebyn. And I'm Taebyn. I'm a pup, bark, bark. So today I want to talk about and give you a few examples of triple integrals. I'm going to assume that you already know the idea of double integrals and setting what it means to have volume in terms of integrals. Really good online resources are wolframalpha.com and desmos.com. I hope I spelled those right. If not, you can Google and find them. Anyway, they're really good utilities. So when you're doing these things, and this, what I'm going to say now applies to double integrals too, what you want to think is for each x or y value, maybe, value in your region, you want to identify what the other variable values range between. The y values, or if you did y values here, this would be x. Y values go whatever to whatever. Let's apply that idea to this example. So the volume, let's call this region, the solid, let's call it D. The volume of D is the triple integral over d dv. Right, because this goes to, I'm assuming you know the volume of the thing is a triple integral dv. There's an invisible function 1 in here, or integrand. But, okay, so this is the volume, and so we want to, by iterated integral, I want to split this up and put the limits of integration on it. So we want to fill in these question marks. And then you can use whatever order of integration you want. Let's see, let's do dz. It doesn't really matter. Dy dx, what are we looking at? So we want to find the volume of the solid enclosed by these two things here. I guess I'm also assuming you kind of know the basics of surfaces and what they look like. This is a paraboloid facing up. And then this one is a paraboloid facing down. And we want the volume in the intersection of those two things. Now, this dz refers to the innermost integral, right? Here's z values. And then the dy is in the middle, so this middle integral refers to y values. I don't know, y values. The y values. And then, of course, the outermost integral will refer to x values. It's really important to identify that because this helps you identify what letter are ranging between what things. We'll see how that works here. The z values go from here up to there. The bottom of this guy to the top of this guy. This is z values. This will be equal to the integral, and again, this is still question mark, question mark, question mark, question mark. So the z values are going from the here up to there. So this guy, we go from this guy, which is this guy. So I'm going to write for my lower limit of integration 5. Remember, this is z value. So this is z equals. This can be really useful to write z equals to remind you. 5x squared plus 5y squared up to this, the top here, which is this guy. 6 minus 7, x squared minus y squared. And then we have the dz, dy, dx. Now we need to figure out these limits of integration. Hi, and I'm back. Sorry, I went away for a second because I wanted to give myself more time, more room to write. So I just moved that up, as you can probably see. this is my z values. Now the dy dx refers to here. And the thing is, these are the values, this is the region R that I'm talking about here. In this case, we have a region R, and we're going to talk about not just x values, but x, y coordinate pairs. Not apples, but pairs. Ha! If I go back here, what's the region R? Well, I've got this intersection circle of where these two paraboloids intersect, right? And so if I, let's see, here's the xy plane, there's the z-axis, okay, great. XY plane, it's not a helicopter, it's a plane. This intersection circle, if I look at it here, this is my region R. This black circle is this region R. So my XY pairs are coming from this region. And again, that just emphasizes the fact of why these limits are like that. The z values, I'm taking an xy pair from my region, and those values go from here up to there. Okay, so again, that's just emphasizing that. So now we need to describe this region R. If I just look at the xy plane, there it is. This intersection is, the equation of this circle is found by setting these two things equal to each other. 5x squared plus 5y squared is equal to 6 minus 7x squared minus y squared. Okay, so we want to see what this thing looks like, so we just simplify. It's algebra. If I add 7x squared to both sides, I get 12x squared. And if I add y squared to both sides, I get 6y squared, and I'm left with a 6. And you can leave it like that, but it's kind of nice to make numbers nicer, so you can divide by 2, or sorry, divide by 6. You could divide by 2, but I'm going to divide by 6. This is the equation of this circle. Or sorry, it's not a circle, it's an ellipse. And it intersects, so again, I'm kind of assuming you know some algebra here, but where does it intersect? Well, it intersects the y-axis when x is 0, which means that y is plus or minus 1. So this is a 1, and this is a negative 1. And then it intersects the x-axis when y is 0. If you plug in a 0 for y, x is plus or minus 1 over square root of 2. And of course, that's just algebra. Hopefully, make sure you can do that algebra on your own. I didn't go through the details here. So this is negative 1 over square root 2. And this is 1 over square root 2. Okay, so now we know what this looks like. These are y and x values. And then these are x values. When I do this, I usually start from the outside in. I'm thinking for each x value in some range, each x value in my x values go range where? From negative 1 over square root of 2 up to 1 over square root of 2. So in the interval, negative 1 over square root of 2 up to 1 over square root of 2. So this is where I'm taking my x values from. When I do these things, I draw what I'm doing now, and I physically do this. So there's an x value. Where do they go? The y values go from here, the bottom of the ellipse, up to the top of the ellipse. So this is actually, this is just thinking in terms of double integrals now. So this is actually a good explanation of how double integrals work, it turns out. But, so for each x value there, the y values go, and I also write out this sentence too, for myself. because this tells me exactly what my limits of integration are going to be. For each x in there, the y values go what? They go y equals the bottom of the ellipse to the top of the ellipse. It's not -1 to 1. That's a common mistake. If you were going -1 to 1, that's every single x value. You're talking about the rectangle, but we're not. We want to go from the bottom of the ellipse. We want to solve for y because we need y equals. So if I solve for y, I get y squared equals 1 minus 2x squared. Then I take a square root. Plus or minus. Don't forget the plus or minus. So you go y equals, the bottom would be the negative 2x squared to the positive. Positive. So that's what gives you these limits of integration. With the magic of pausing and erasing things, I apparently need a bigger whiteboard. So I erase all that stuff just so I could write the last line here, which is, this will equal an integral dz dy dx, and I still have this stuff. So this is 5x squared plus 5y squared. Then I have this guy, 6 minus 7x squared minus y squared, dz dy dx. dz. It makes me dz. Ha! That was dumb. Okay. dy. Okay, so these are, here's my x values. My x values are going here. -1 over square root 2 up to 1 over square root 2. And then the y values go from that guy up to that guy. Just like in the circle. And that's it. And then you can evaluate that integral and you get a number, and that number is the volume of your solid. So I want to emphasize, it really helps to write down this sentence. For each xy pair or yz pair, whatever, in blah, those values go from thing to thing. Or if you're doing a double integral like this, reduced to, for each x value in blah, or y value, whatever you're doing, you really need to be able to write this sentence down. Because once you can write this sentence down, then you can write your limits of integration. And this type of stuff it just takes practice to do problem after problem after problem. But I hope this has helped explain the ideas. Okay, so I want to do one more example with triple integrals. So let's get right to it. Let's do another example. This time, it can often be useful to change the order of integration, because sometimes whatever your function is that you're trying to integrate, because of the way the order of integration is, you actually cannot integrate it. In that case, it can be useful to change the order of integration, and then you can integrate it. If your function is continuous over the region, if it's continuous, there's a theorem that says you can change the order of integration. If it's not continuous, you can't necessarily change the order of integration. So I'm not going to care what function I have here. I just have a function, and I'm just going to say it's a continuous function, which means I'll be able to change the order of integration. And let's say I wanted to change this to dy dx dz. So let's kind of see what we've got here. If I draw this x, this is an x, y, z. And this function, I don't know what it looks like, but you've got like a Superman cape or something flying around up there. Just like I said before in the previous example, here's my x values. And then y values are in the middle. Y values. And then the z values are in the end, or on the outer integral. Okay. So this is saying for each YZ pair in my region. So the thing is, I've got this region in the YZ plane. So I've got this region somewhere in the YZ plane, which we can identify, which we'll do in a minute. For each YZ pair there, I want to know, what do the X values do? X values go, and then you have to identify where they go. See, so I'm trying to write down what this is. Then once I do that and identify this region, the solid, the whatever, the thing, then I can switch the order of integration. So this is x equals 2y. So the x values go x equals 2y up to x equals 2. X equals 2y is, in the xy plane, it's x equals 2y. We'll look, I know, something like this. And then x equals 2. And so, but this is a plane, because there's no z value, so z can be whatever it wants. It can be a teacher, it can be a fireman. X equals 2. The z values go from 0 to 9. So that cuts this off. And then my region is going to be this, my region R will be this rectangular region, kind of projected on the YZ plane. So my YZ pair are coming from here. And the X values are going from this blue, the X equals 2y plane. Just think of it like a wall coming out here, kind of diagonal. And the XY values are going from the wall to the wall that is x equals 2, right? So it's coming from, not from the YZ plane, but from the wall, the x equals 2y wall, out to x equals 2. So then, if I want to change to this order of integration, the new region that I'm looking at, I'll call it S, is in the xz plane. Integral, 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 and then my function f, I'll just write f, dy dx dz. Like I said, S. And that region S is in the xz plane. Here's the xz plane over here. And so that's going to look like this rectangle. I'm taking this wall and projecting it onto the xz plane. And this is my S. Now, in this setup then, let's write down our limits of integration. So these two are referring to S. And in S, these are z values. So these are z values here. X values are in the middle. And then y values are on the inside. X values, and then y values. Okay. Now, again, several ways to think about this, but really when it comes down to it, I'm thinking, sorry, I keep going back and forth. It's fun. I'm getting exercise. Exercise. Pop. For each xz pair in my new region here, S, what do the y values do? Again, as I keep saying, write down this sentence. This really helps you identify what your limits of integration are. Y values go y equals I'm going to identify now to y equals. As soon as I fill in these blanks here, I'm done, close to done. If I get out of the way, for each pair in here, in S, I'm going from, my y values go from 0 out to my wall. So they go from 0. What's my wall? Well, my wall is x equals 2y, but I need y equals something. So just solve for y. Y equals 1/2 x. So I go up to y equals 1/2 x. So now I can identify this is a 0 up to 1/2 x. Good. Now I have to describe the region S. In the same way, for each z value from 0 up to 9, so it happens to be the same numbers as before, as we started with. But now, the z values, z, in the interval 0 to 9, the x values go x equals, where did they go? They go 0 up to 2 now. So that means that this is 0 up to 2. Notice this upper limit of integration has changed from 1 to 2. But this is it. Yay, fun. It's fun. It's really cool, fun stuff. And as I said before, you just got to practice. And it's lots of good stuff. Yeah, good. So I hope you've had a fun time with me today. I know I have. Have fun just practicing doing lots of double and triple integrals. Doubles help you with triples, of course. And I'll see you next time on Math with Taebyn.